What clicker do I use to? How do I advance? This is
Right.
Can you make it?
Yeah, I'll make it huge.
Sorry.
So let me make sure we're all right. Recording is going. All right, our 3 o'clock. Let's get started again. Our next speaker is Vlad Pribitkin. Simple upper bounds.
Thank you, Kevin. It's a pleasure to be here. And I first want to thank someone who's not here currently, but maybe I should lavish more praise on him then. He certainly deserves it for all the organizing that he's done over many decades. And also thanks, Mel, for answering emails. Yeah, my talk will be very easy. I think the easiest talk I've ever given. I would never have given this talk when I was younger. So the partition function, as we all know, counts the number of ways of expressing positive integer n as a sum of positive integers with repetition allowed and without regard to order.
We
I
don't
have
see
some.
the slides.
I have. Excuse me. You can't see the slides.
That would be my fault.
They exist.
And can you see them now? Hello?
Yes.
Yes, thank you.
Okay, so you didn't miss much. I defined the partition function, and now I'm about to do some definitively non-random examples. P of 12 is 77, P of 22 is 1002, and the next and perhaps most important hint, P of 1887, which is an important year here, is equal to this 45-digit number. 1887, you can check, is congruent to 6 mod 11, which means thanks to the person I'm honoring by giving his birthday, this 45-digit number is divisible by 11. Another non-random example, P of 8,849 is the first instance where the number of partitions goes over a Google. I did not do these by hand. Okay, so at the bottom we have the generating function thanks to Euler, which I think everybody knows. So let me continue. The next slide gives some estimates and formulas for P of n. Very crudely, we can bound P of n by the number of compositions, which is exactly 2 to the n minus 1. That's trivial. There are good upper bounds. A good upper bound is P of n is less than e to the pi square root of 2/3 times the square root of n. This was done independently, I believe, first by Erdős in a well-known paper where he did much more. He used induction, starting with a recursion formula. I know that Mel knows about this very well because he's generalized this method of Erdős's. And then independently, but not published, by Siegel, who used, he just used the generating function. Used a generating function and did it very simply. It's calculus. And that is the theme for my talk. It is simply calculus. I will use nothing beyond that. Also, I want to thank Mel because although I had seen Siegel's proof before in my advisor's book, Marvin Knopp's book on modular forms, and also in Apostle's book, it did not give attribution to Siegel. It's from your book that I learned that Siegel did it and he lectured about it, but he never published it. I got enamored by this as a graduate student. I thought surely one could do better and still retain the calculus intention. So eventually I proved that you can give an upper bound where you divide by n to the 3/4. And the proof is still quite easy. I just use Ziegel's idea and I tweak it. I did use dialogues. So that was the new ingredient of a functional equation for the dilogarithm function. There is the timeless asymptotic by Hardy and Ramanujan, and then a couple years later, independently by Ouspensky. And you can see that the bounds given above are pretty good compared to the asymptotic. On the asymptotic, we divide by a constant times n. And at the very bottom, I'm mentioning the exact formula, which is due to Rademacher, who was my mathematical great grandfather. And also, we share the same birthday, separated by 70 years. I just gave away my age. He, maybe some of you know this story. He came up with this. Well, he was preparing his lectures for his class at University of Pennsylvania, and he thought he had made a mistake, that he could figure out this exact formula. And because he thought he made a mistake, he gave it as an assignment to his students to find the mistake. Well, I guess they're still working on it. But I know this for a fact because Marvin Knopp told me, and Marvin Knopp knew this from Joe Lehner, who was in the class. And I also knew Joe Lehner. He lived to be over 100. I threw in that I have it's a bit of an exaggeration, but a simpler proof by totally different means. The circle method is fantastic. Don't get me wrong. It's launched 1,000 papers. But if one uses Poincaré series of dual weight, instead of looking at the weight of this modular forms here, the weight of the reciprocal of the Dedekind function is -1/2. If you look at the dual weight, which is 5/2, and use the theory of Poincaré series, you can pretty quickly get the exact formula, and I consider it to be significantly simpler. Okay, let me continue. Let's go on to the subject of this talk, the power partition function, P super R of n. This is the notation used originally by Hardy and Ramanujan, and that's why I'm using it, even though it looks a bit odd. It's a number of partitions of the positive integer n into perfect rth powers, where r is greater than or equal to 1. Let's do some non-random examples. The number of partitions of 1729 is this 43-digit number. The number of partitions of 1729 into perfect squares is this 13-digit number. Of 1729 into perfect cubes is this 7-digit number. And you can see the trend. Once you get to perfect eight powers, it's equal to 7. And from 11 and beyond, there's just one partition. Okay. Well, 1729, as we all know, is very famous. The taxi cab number. It also happens to be a Carmichael number. Carl Pomerantz, who's here, will tell you all about them, since he proves there are infinitely many. The third smallest Carmichael number, I believe. I happen to go on OEIS, which I know about now from people like Mel and from George Andrews, and I was looking at the list of the cubic partitions, and I noticed that 1729 appears on this list. So this is what I'm calling an amuse-bouche for you, in case you are bored. The number of partitions of 397 into perfect cubes is 1729. Now, I got curious about the number 397. I did take a cab ride here today, but that was not the number on the cab, although it was strangely close. And I started thinking a little bit about 397. What could I come up concerning it? Well, very low hanging fruit, but it is a prime. It is, because it's a prime, it's congruent to 1 mod 4. It is the sum of 2 squares. It is the sum of 3 squares. It is the sum of 3 cubes. It is the smallest prime that is the sum of 3 cubes congruent to 3 mod 4. It is a difference of 2 cubes. It is 12 cubed minus 11 cubed. When you think of 12 cubed, it brings you back to 1729, which is, of course, 12 cubed plus 1 cubed. So gathering up all these facts, I think perhaps 397 is a worthy number. But you guys can think about it and let me know. Okay, at the very bottom, that's it for the tangent. At the bottom, we have the generating function for the power partition function, which, of course, is again by Euler. Here is the asymptotic formula for P super R of n. It was stated by Hardy and Ramanujan, but as far as I know, they never proved it, at least not in print. But in the early 30s, Wright, who was Hardy and Wright, Hardy as in Hardy and Wright, one of Hardy's students, he did prove it. And he proved much more than what I'm getting here for the asymptotic. So you can see the formula there. There are 3 noteworthy features. If you look at the numerator, it's e to the power c sub r times the r plus first root of n. The denominator is a power of n. It speaks for itself. And then there's the constant a sub r, which also speaks for itself. Oh, I should mention that both c sub r and a sub r depend on what I'm calling a b sub r. That's important. It is the product of the gamma function times the Riemann zeta function evaluated at 1 plus 1 over r. Okay, this is asymptotic. And since I worked on an upper bound for P of n, I thought, let's see what I can do with P super R of n. But it has to be in an easy way. That's my rule. Otherwise, I'm not interested. Unless if I can get an exact formula, which doesn't exist, then I would be interested. Okay, so here's what I'm calling a surprisingly good upper bound. It's not published. It's not yet published. It will be. So with notation being the same, here is the upper bound. It's good for all n greater than or equal to 1. So let's dissect it. If you compare it to the asymptotic, which I just gave, the numerator is exactly the same. If you look at the denominator, namely the power of n, it's close. It's just off by a term of 1 over 2r plus 2. So it's good. And then there's the a sub r, what I'm calling capital A sub r. It's the constant. It's not as important. In fact, I can improve upon this, but this is what I got using very easy methods, which I will show you. I want to show some special cases here. I want to be careful with time. These are the cases for articles 1, 2, or 3, just to hopefully impress upon you how decent the bound is. For P of n, it shows that it's less than a constant, which is itself less than 3/5 times e to the power c sub 1 squared of n divided by n to the 3/4. So it's a bit better than what I had mentioned earlier that I came up with using the dialogue. For partitions into perfect squares, give this bound. You can see up top in the numerator you have e to the a power of something times the cube root of n and dividing by n. So to compare this to the asymptotic, the denominator is off by 1/6. For P of n, it's off by 1/4. For the first squares, it's off by 1/6. If we go to perfect cubes, I give the result here. And again, for comparison's sake, the denominator now is off by 1/8 compared to the asymptotic. Okay, now I know the burning question here that you've already read perhaps is, what about partitions of n into perfect Zenzics, and the like? Well, let me tell you. Zenzic means perfect 8th powers, as everyone can tell you. Okay, if you're bored, you can read my footnote. It is the word that boasts the most Z's that's in the Oxford English Dictionary. And it was coined in the mid-1500s by a guy named Robert Record. And he also came up with something that I think comes up in pretty much every math talk, the equal sign. So I didn't know that. In case you didn't know it, I thought I'd pass it on.
Is that really true?
Yes, this is true. That is true. As far, I mean, unless if I've been lied to by, the internet, and how could that possibly be? But that's true. So if you didn't know, I'm happy to have come up with something you didn't know, Mel. Let me get back to where I want to be. Yeah, so I give the result for P super 8 and also 24th powers, Zenza, cubics. Yes, I checked it. Yes. Yes. Okay, let's look at the proof, because I want to convince you that it's simply calculus. We have the generating function for the partition function I'm interested in, because I want to do calculus. I'm restricting x to be a positive number less than 1. Okay, the first observation, which is easy, is that everything is easy once you see it. And I think actually in math, everything is easy once you see it and understand it, but it's hard to prove that. Donald Newman was one of my professors, and he imparted that philosophy to me, and I believe it. Okay, so I went on a sidetracking, sorry. The partition function is positive and it's non-decreasing, so you can exploit that and see that h sub r of x is strictly greater than the partition function times this infinite geometric series, which sums to x to the n over 1 minus x. So we instantly get this upper bound. This is, by the way, using Siegel's idea and tweaking it and then doing something differently, which I will tell you about. P sub r of n is strictly less than h sub r of x times 1 minus x times x to the negative n. Okay. We want an upper bound on what I'm calling h sub r tilde of x, which is the product of h sub r of x times 1 minus x. When we take the log of that quantity, we get this infinite series. If we can find a good upper bound on this infinite series, then we'll get some kind of result, hopefully a good result. Now, right here, what should one do? Well, especially if you're an analytic number theorist, which I suppose that I am, been doing it for some decades. You look at the log function, and it's dying to be replaced by its infinite series, right? So put in its infinite series, do the interchange. That's what Siegel did. That's what Hart and Ramanujan did sometimes. It's the reasonable thing to do. Yet when I did it, things weren't working out so well. So instead, don't do that. Don't put in that infinite series. Let's go to the next slide. We're going to let x equal e to the minus c. Well, that you could do regardless. And now we're going to use some calculus which we teach to our students, in particular, the integral test. We're going to exchange the sum, the whole sum, with this integral. So you see the infinite sum starting at 2. If you look at the function, the negative log of 1 minus e to the minus y to the r of u, that function is positive, it is strictly decreasing, and it is concave up, which means we can inscribe trapezoids under it, and those trapezoids give us the sum that we're after, so we get this upper bound on it easily. We take the infinite integral, we break it up, we write it as negative integral from 0 to infinity plus integral from 0 to 3/2. The first integral you can evaluate pretty easily. That's where the gamma times the zeta function pops up. And the second integral, you can bound it, the different ways of bounding it. I use the bound from essentially, I think, pre-calculus. So I wanted to make it as easy as possible. Then you use integration by parts to evaluate that integral from 0 to 3/2, and you get this expression. Combining this upper bound on h sub r tilde with what we had on the previous slide, the upper bound for p super r of n, we now have an upper bound on p super r of n in terms of u and r. Okay, now it becomes Calc 1, differential calculus. We're free to pick u to be whatever we want. I pick a clean value, meaning this is not the exact critical point, but if you look for the exact critical point, it's slippery beyond r equal to 1. And if you plug in that number, you get the upper bound that I checked. So it is calculus. It's not a lie. Okay. So that's the proof. I think I still have a couple minutes, right? Yes. Okay, so let's generalize it a bit. So here's the generalized power partition function. P super r of nma. This is the number of partitions of the positive integer n into parts from the set a to the r, n plus a to the r, 2n plus a to the r, etc., where r, m, and a are fixed positive integers. Okay. The generating function, again, thanks to Euler, is what's given there. To get a bit of a feeling for this generalized power partition function, here's an easy observation. If you look at the GCD of A and M, let's call it D. If D to the R does not divide N, then this partition function is 0. If D to the R does divide N, then you can express this partition function in terms of another partition function. And this is a somewhat long way of saying that in anything you do with this, it's safe to assume that A and M are relatively prime. Okay, same question I asked before. Can we ascertain a decent upper bound on this partition function in an easy way? Well, the answer is yes. So here is, now the other one was a surprise, so now this should be not a surprise. This is unsurprisingly good upper bound. And I give it here, I'm assuming that A and M are relatively prime. There can be no partitions if N is less than A to the R, so let's not have the theorem look stupid. So I'm assuming that N is greater than or equal to A to the R, and I give the details here. It's very similar in feel to what I gave before. There are three parts. The numerator has e to this power that involves the r plus first root of n, and then times c. Essentially, what's happening here is that n gets replaced by n over m. That's exactly what happens, and that's all that happens in the top. The starting base does not affect the numerator at all. It does affect the denominator, and you can see there how it affects the denominator. And then I give capital A. It depends on R, M, and A. Both C and A depend on B sub R, which is the same product I gave before of the gamma function times the Riemann zeta function evaluated at 1 plus 1 over R. What's the proof? It's calculus plus what I deem common sense. You have to be a little bit careful because this function is not always positive, but it is always non-negative. It's also not non-decreasing. However, it is non-decreasing on a certain subsequence. And that allowed me to do basically the same proof. Okay. Here is a sample consequence. Now, since there are three parameters in play, R, M, and A, you can write down many examples, but here is one I chose. When R equals 1, I'm getting what I'm calling P of NMA, the number of partitions at n in which each part belongs to the arithmetic progression, Jm plus A, J going from 0 to infinity. I'm assuming that A and M are relatively prime, and you get this bound, this upper bound. The details are given. Again, if you compare this to the upper bound that I gave for the partition function, the C sub 1 is the same, pi times the square root of 2/3. N up top gets replaced by N over M, and the bottom is a bit more complicated. If you compare this to the asymptotic that's known, it's not bad. The numerator is exactly the same. The denominator is off by 1/4 in the power of n. Okay, and if you do a super specialization or specialization, look at P sub odd, the number of partitions of n into odd parts, then for all n greater than or equal to 1, you get that P sub odd of n is less than this constant, which is a touch larger than 2/3 times e to the power C sub 1, the square root of n over 2, divided by the square root of n. If you look at the denominator, it's compared to the asymptotic. The asymptotic is n to the 3/4. So it's pretty good considering the methods that I used. Okay, and as a lagniappe, a word I learned from a book by George Andrews, means bonus. You get, thanks to Euler, we get an upper bound on Q of n, the number of partitions of n into distinct parts. So this is, as I said, a sample consequence, but there's nothing that I did here that could not have been done by Euler. All the methods couldn't be done before Euler, but everything else certainly was known to Euler. So that's it. I don't have a slide that says thank you, but I do thank you. I especially thank everyone here who might be from England or Argentina. Thank you very much.
You brought that up. I don't want to know how the game will be over when I get home, but I'm taping it, so I don't want to know how it.
I was about to ask, what's the score?
No.
I didn't ask what the score is.
Do we have questions for Vlad that are not soccer related? From Zoom? It was so clear.
I don't know.
And surprisingly simple. Let's thank Vlad again.
Oh, I have a question.
And our next talk will start So Trevor, how fast can you walk up here? Yep.
Have to find the USB.